Okay, this is the second part of chapter 2, dealing with resonance. So, just to repeat, the idea of resonance is that, especially now, from now on, we're going to speak about resonance, which is acoustic resonance, vibration of an air column in response to an applied frequency or to an applied vibration. In this case, the vocal tract is our tube, is our filter, is the acoustic resonator. And it is down, it ends with the vocal folds on the end. So whenever you speak, the vocal folds are completely like meeting each other like this and closing the end of the vocal fold. And then the buzz goes through them, but the nothing goes back. So then the column inside of that space in the pharynx or the vocal tract vibrates in response to that original vibration. So the vocal folds produce the fundamental frequency, which is called the applied frequency or the driving force. And that one is going to produce harmonics or the resulting vibrations of the air in the vocal tract, which is the resonator. We said before that the length of a resonator, the length of a tube, is going to also influence the nature of resonance, how if it is going to be a high tone or a low tone. Also the diameter of the tube is going to affect the resonance. So when you look at the human vocal tract, it has three tubes together that are connected. It has the vertical tube, which is the pharynx. It begins right above the vocal folds, and it goes up to the end, the posterior end, the back of the nasal cavity. So this pharynx, the area that is next to the vocal folds, or right above them, is called either the hypopharynx or the laryngopharynx. You must have learned this in your anatomy. The oral cavity, the area of the pharynx across from it, is called the oropharynx. The top area of the pharynx that is in the nasal cavity, it is the posterior end of the nasal cavity. So these three parts, the nasopharynx, oropharynx, and hypopharynx, make up that vertical tube that is the pharynx. Then you have the oral cavity, which is another small tube, and then the nasal cavity, which is the third tube. So when you make a sound, it is in many cases it will vibrate, like say when you say it will vibrate through the entire tube. Now recall, what is the difference, or one of the differences between a narrowly tuned resonator and a broadly tuned resonator? One is in the shape. A narrowly tuned resonator is very symmetrical, like a cylinder. Everything is perfectly, symmetrical. And that wouldn't accept many frequencies. It wouldn't amplify just anything that goes through it because it has a restricted range. If you are not close to the natural frequency of that tube, you have no chance of being amplified. But the other side, the more irregular a shape or a tube is, the greater the bandwidth. In other words, if something is more irregular, it will be more broadly tuned. So now, the pharynx itself, yes, it is irregular. It has different width, widths, the bottom versus the middle versus the top, and in the meantime, the vocal tract itself is also irregular. And then the nasal cavity is irregular. So you add all of these three things together, it will give you a very, very irregular tube that makes it quite very much of a, creates a big bandwidth. That means it can accept many, many sounds that you make down there, and they will be amplified by the vocal tract. So, the average child, we are speaking about children, from birth to about 10 years old or so, or maybe 13 even. The average is 6 to 8 centimeters in length. Centimeters, 1 inch equals 2.5 centimeters. So the average vocal tract from the vocal fold to the lips is 6 to 8 centimeters for a child. For an adult female, the average is 14 to 15 centimeters. And for the adult male, you have different counts based on the size of the head and so on. Some research will tell you 17 to 18 centimeters is the average, and some research says 17 centimeters. So it doesn't matter to us because both numbers are fine. So, and I'll give you questions, when we have problems here, you'll have an exact number. It will not be an average. I'll say, there's a female that has a 15-inch vocal tract. What is her resonant frequency? And then I'll give you numbers. We will figure out how to calculate resonant frequency when you are given these values. So let's look now at the vocal tract and how we can calculate. If you know the length of it, we will, of course, give you clues. Then you will be able to know the resonant frequency of that vocal tract. So we said that the vocal tract is closed on one end. It's a 1/4 wave resonator. That means the first time that the vocal folds will make a sound, that sound is that wave is only 1/4 will fit in that tube. So if you know the length of the tube, you'll be able to figure out the length of the entire wave. If you get, the length of the wave, then you can figure out the resonant frequency of that vocal tract. And it acts as a band pass filter. That means the sound that is amplified is within the range, within the lower cutoff and the upper cutoff, and then a lot of the stuff now is attenuated. So it gives you maximum enhancement of the sounds that come within the natural frequency or within the bandwidth of that tube of the vocal tract. So it eliminates a lot of noises and things. So the vocal tract, again, as I explained, consists of 3 cavities linked together, and that maximizes the number of frequencies that it can take, it can amplify. In other words, it can accept it will have a wider wave. It would have a wider range of amplification between the 2 cutoffs. So the resonant frequency of the whole tube, of course, is the sum of all the combinations of these 3 tubes that are connected. Now, how can you measure the resonance of the vocal tract? You have to put a tone in there, but you want to see the vocal tract at rest. Like, how do you measure it when it is resting? The only way you can do that is to, if you want to do it at rest, is to insert a tube, have a surgery, insert a tube here, and make a sound that goes up, and then while the vocal tract is resting, and then you measure the frequency of it. But of course, that is not realistic, you know, to go and have a surgery, have a machine and make a sound. So the only way is to make the smallest sound possible and have it go up, you know, through the vocal tract, and then measure the vibration rate of the vocal tract, of the air inside of the tube. And the sound that makes the smallest movements and the smallest change in the vocal tract is the schwa sound, as when you say about, for example, about. So when I say about, the at the beginning is the schwa, or you say above, above. So it is almost like neglected. The vocal tract is almost at rest. For this reason, we use the schwa as the base measurement to measure the vocal tract resonance. And then that is usually 500 hertz for the average person. So the vocal tract, the first resonant frequency of the vocal tract occurs when the sound, vocal folds make that sound, say schwa, or any other sound. The vocal tract is going to only respond when that sound wave starts to come close to the length, to the vibration rate of the vocal tract. We said that the sound, you make a sound and it starts to echo and echo and echo and echo, and as every time it plays again, it becomes higher frequency, higher frequency, higher frequency. These are the harmonics. So when the sound wave, as it continues and it becomes higher and higher frequency, the time that it reaches the close within range of the vocal tract, then the vocal tract is going to start to take that sound and amplify it. So every vocal tract or every tube is going to respond at a certain time in the process. When you make the tone with the vocal folds, and the first time that the vocal tract is going to respond, it will respond only when the wave, a quarter of that wave, fits into the vocal tract. When the wavelength of the wave is 4 times the length of the vocal tract, that's the first time that the tube, that the closed tube resonator is going to respond. So now, because the vocal tract is an acoustic resonator, it is a quarter wave resonator, it is going to be selective. It will act as a filter. So you remember the standing waves. It is going to selectively take out, eliminate certain frequencies, and then it will leave certain frequencies, and this way it will enhance and maximize the sound. So again, it will leave the odd multiples of the lowest resonant frequency, and it will eliminate the even ones, and then I'm going to explain how. What is left, or the vibrations that the vocal tract is going to leave and enhance, are called formants. So the formants are the enhanced or the vibrations that are echoed, that are played by the vocal tract. And they're the first, the vocal tract, because it's a broadly tuned resonator, it can produce, or it can amplify up to 40 formants. So that's a huge number, because again, it is broadly tuned. And every time, the first formant is the loudest of all, and then the second is going to be a little bit less. And as you keep going, they become less and less and less and less until the sound just dies down. what you hear in the end when someone speaks is the summary of all these formants combined together. But because the first formant is the strongest, is the loudest, and the second and the third, then these three are the most important formants in the entire series of harmonics, of vocal tract harmonics. So the first three. Sometimes we look at the fourth one, but when we study vowels, but the first three formants in the vocal tract are the most important, the loudest. They determine most, they make up most of what you hear. So let's see how this works. We said that the buzz, the sound that the vocal folds actually generate, the tone or the wave, we call it the fundamental frequency. That is the mother of everything else. Everything comes out of it. Then the first harmonic is the first vibration of the vocal tract, the air inside of the vocal tract. The second harmonic would be the third vibration. The second harmonic will be the second vibration of the air inside of the vocal tract. So it's like that guitar string. You make the sound, you let go of it, and the guitar string, and then every time it makes a wave, it becomes twice high in frequency. Every time it makes the second wave, it starts to decrease in frequency, and then it will decrease, increase in frequency, it will decrease in loudness as you go. But the trick here is that we do not necessarily always know when the air is going, the acoustic resonator, the air column, when is it going to respond? Because it will only respond when the wave comes within range. And we said the wave as it is played is going to increase in frequency. So if we say the vocal tract resonance is 500, and then the vocal fold resonance, let's say for an adult male, is like, say, 100, that is a huge difference between the two. So the wave, the vocal folds are going to continue to go into their harmonics, where the vocal fold, as it vibrates the first time, the entire vocal fold will vibrate. The second time, half of it will create waves that are twice as high, but less loud. And it continues to raise frequency and then decrease loudness to the point when it reaches close to the 500, within the range of the bandwidth, then the vocal tract is going to start to pick up and to amplify the sound. So for that reason, it doesn't matter at some point. Once you get the first response from the vocal tract, once the air in the vocal tract begins to resonate, give you the sound back, then that is going to determine what happens next. Everything, all the subsequent frequencies are going to be determined not by the fundamental now. They will be determined by the first time that the vocal tract begins to buzz, begins to play the tone. I hope that you understand this difference, because it is critical when we calculate now the resonance of the vocal tract. We no longer look at the F0. We no longer look at the fundamental frequency. We look at the first time that the air column in the vocal tract begins to resonate. We use F1. We use the first resonant frequency as the basic for our measurement. Everything that comes after it is a multiple integer of the first formant. So we call these F1, F2, F3, and so on. So to determine the wavelength, we first figure out the length of the vocal tract, because we are going to calculate now what is the resonant frequency of this given tube. So for example, if there's an adult male, he, has a vocal tract that is 17 centimeters long. How long is the wave? How long, what is the resonant frequency of that vocal tract? You simply say, oh, the wave, first we need to figure out the wavelength. So the wave is, because it's a closed tube resonator, only 1/4 fits at first. So we say if the tube is 17 centimeters, then 1/4 is going to fit the first time. So that gives me 1/4 of the wave is 17 centimeters. Now I can figure out and say, oh, if 1/4 is 17, then the whole wave is 17 plus 17 plus 17 plus 17, or 4 times 17, that equals 68 centimeters. Let's just make sure that the number is correct. So 4 times 17 equals 68. So now we figured out the length of the wave, and from there it becomes even easier. The wavelength and frequency, as I mentioned before, they are related. So frequency equals the sound constant, which is the speed of sound, the treble, divided by the length of the wave. We now have the length of the wave, which is 68 centimeters. Now, the tricky thing I told you about before is that the sound constant that we learned, 331 meters per second, it just was the generic. It applied to any sound under 2 conditions, sea level and freezing temperature. We as human beings can't make a sound when our body is frozen solid. So there's a difference in temperature of the body and the room and all of this. We don't need to get into any of these calculations. But the sound constant, the speed of air and the speed of at which sound travels in the vocal tract is 340 meters per second. So now, it would make sense if you want to, to divide 340 meters. You divide meters by meters, it would make sense. But we are measuring the vocal tract in centimeters. So if you divide meters by centimeters, it will give you a very strange number. It's not going to make any sense. So as a result, it's like dividing dollars by, by a number of people versus dividing pennies by a number of people. So in any case, because the vocal tract is measured in centimeters, that sound constant of 340 has to be converted into centimeters as well. So you say 1 meter equals 100 centimeters. So 340, you add 0, and you get 34,000 centimeters per second. So that is the same, like the sound travels at the speed of 340 meters in, when humans make it in the vocal tract. And you can say the same thing. Instead of saying, I'm going to give you $5, you could say, I am going to give you 500 pennies. It is the same thing, but you phrase it in a different way. But when you speak about centimeters here, you have to convert the 340 to centimeters per second. So that will give you this equation. The frequency or resonant frequency of the vocal tract now equals sound constant divided by lambda equals 34,000 centimeters per second divided by 68 centimeters per second. Now calculate and see what you get. That will be your wavelength. Let's see. So 34, 1, 2, 3 divided by 68 equals 500. That will be 500 hertz. So that man's vocal tract is going to resonate at 500, or the natural resonant frequency is 500, and any, of course, sounds that come closer to the 500 will be amplified. Sounds that as they go away from that 500, they become less and less loud. So now we'll take the same person. 500, when you have the harmonics series that we showed in class yesterday, when we started and said the fundamental frequency is in the far left, and then everything else that comes, from there, like if you have fundamental frequency of 100, the first harmonic is going to be 200, the second harmonic will be 300, and so on. And we said that we labeled the lines, the individual frequencies, indiscriminately, 1, 2, 3, 4, 5, 6. So we started with the fundamental, said 1, and the first harmonic we said 2, and 3, and so on. So now, in this case, let's see. In this case, the fundamental, the first harmonic is going to determine everything that comes after it. In that case, it will take the place of the fundamental frequency. So we know now the vocal tract is going to respond, the best response for the vocal tract that is going to determine everything else is 500 hertz. So instead of the fundamental now, we just delete it and we put F1 and we say that is the first resonant frequency, the first vibration in the series is going to be the fundamental frequency. So that will be F1, 500. Then F2 would be twice as high. F1 is the first vibration, the fundamental, what do you call it? It acts like the fundamental frequency, the bass. So the resonances that occur after it are going to be the first one that comes after that is twice as high. So if you say 500, the next one is going to be 1000. You still now count the numbers as 1, 2, 3. So the second vibration, let's call them R1, R2, R3, like resonance number 1, resonance number 2, resonance number 3. So the first one is 500. Second one is going to be 1000. So 2 times 500 is 1000. The third one is going to be 1, 2, 3. 3 times 500 is 1500. The fourth one is going to be 2500. And you keep going, similar to what we did before, but the bass here is the first harmonic. That is the bass. That is the first time the air resonates, and that determines everything else. So we'll see how the vocal tract filters and selectively just deals with these. We are calling these F1, the first vibration. We are calling it for the time being R1, just a resonant frequency number 1, number 2, number 3. So the way that the vocal tract is going to behave, it is going to selectively take out the even numbers, like first vibration that occurs, What comes after, we call it R1. That's an odd number. The second vibration that occurs, number 2, is an even number. That is R2, 1000. The third is an odd number, 1500. So the vocal tract as a quarter wave resonator is going to take out, to attenuate the even numbers. Like 1000 will be attenuated, and 2000 will be attenuated, 4000, 6000, and you keep eliminating the even numbers, and what continues to stand are the odd numbers. These odd numbers are the ones that remain and are amplified. These are the ones that we call formants. Formants. So when we say F1, the first formant, F2, the second formant. However, F1 is going to be that first odd number. F2 is going to be the third line originally, but because the second one is eliminated, then we are going to just go from F1. F1 is the first vibration. Second formant is the third vibration. Originally should have been the third vibration. And then F3 is what would have been the fifth vibration, number 5. Because we have eliminated the odds, the evens, and the odds that remain, we call them formants. So even numbered multiples yield opposing forces in these standing waves, while odd multiples reinforce the intensity of the sound. So we'll do more exercises in class to figure out how to calculate the formants. So formants in the vocal tract, they change. The values of them change depending on the cross-section of the vocal tract. If someone has a vocal tract that is wide, then you have lower formants, lower frequencies. If someone has a vocal tract that is long, someone has a longer neck, that person is going to have a more of a deeper voice. That will change the formant. And how the tongue, how the jaw, how the velum, how the articulators behave, that is going to modify the formants in the vocal tract. Resonant frequencies in the vocal tract, they relate to certain locations. For example, they have to do with the areas of maximum pressure and maximum velocity in the vocal tract. So for example, we're going to find out that F1, or the first formant, is going to occur in the lower pharynx. Second formant is going to occur just near the alveolar ridge. The third formant is going to occur just around the area where you say ka and ga. Just because of the nature, the shape of the wave, as it reaches, these locations, it takes in a certain shape. So, first formant means the vocal folds make a buzz, and then the first time that the air inside of the vocal tract is going to resonate, of course, is when it reaches 500. Because that is the vocal tract resonant frequency. So that first time that the vocal tract is going to resonate is when the wave reaches when the wave reaches 4 times the length of the vocal tract, when 1/4 of the wave can fit into the vocal tract. So here here's the closed tube, that's the closed end of the tube. And then that's the open end. That's the first time that the sound comes. So now you have 1/4 of the wave fitting in. And the reflected wave is on the other side. Doesn't matter, but the maximum point of pressure is going to be right at the end, the closed end, which is right at the vocal folds. That will be the maximum point of pressure. And the maximum point of velocity is when the air just goes the fastest, with when the air is like atmospheric pressure. That is at the lips. So the entire tube here, from here to all the way to the lips, has 1/4 of the wave, and it is almost symmetrical, and it has 1 point of maximum pressure, 1 point of maximum velocity. Then the wave is going to echo again, will play again, but this time it's gonna be much higher. So when it reaches twice, like, you know, ideally it should play like if it were to play again, it will be, this is the R1, and if R2 was to occur, then you would have half of the wave fitting in, 1/4 plus 1/4. So you'd have half of the wave fitting in. But we said that that is an even number. R2 is an even number. That will be deleted. So you go to the third harmonic, which is the third resonant frequency. At that time, the wave will be 3/4. The size of it will be 1/4 plus 1/4 plus 1/4. So you have now 1/2 of the wave here, and the other half here. I mean 1/4. So 3/4 of the wave fitting in, and you could see that will be a maximum point of pressure here at the vocal folds, a maximum point of pressure near the, when you say kahanga, in the middle of the oral cavity, and then you have a maximum point of velocity in this area and at the lips. So again, you have it here, the same way plotted. And then the fourth time that should have occurred, it would have been called R4, but we said that would be an even number, where that you'd have two waves completely. I'm sorry, the 4/4. Then one entire wave completely fitting in, but that yields opposing forces, and that is eliminated. So the fifth resonant frequency is the resonant frequency when you have 5/4 of the wave fitting in. The wave has become small enough so that you have 5/4 fitting in, and in that case you have a maximum point of pressure, a maximum point, a maximum point, 3 maximum points of pressure, and 3 maximum points of velocity, and that is R5 or resonant frequency number 5. So what is left now? R1 is called the first formant, F1, and with a capital F. The second formant is R3, the third vibration, and the third formant is R5. Now, could you guess the fourth formant? I mean, the third formant. What will it be? It's just going to be R7. It has to be odd. So now, these are the characteristics of each formant. Number one, because the first formant, as it occurs, the first time the vocal tract is going to buzz, to vibrate, the entire vocal tract will be enough for 1/4 of the wave. Is going to fit in. And you could see it is virtually symmetrical here, So it has only 1 point of maximum pressure, 1 point of maximum velocity. That first formant is often, and if you look for it and measure it in the posterior lower pharynx. So in the back here, behind the tongue, lower in this area is gonna be F1. So any change in shape in this area is going to affect F1. It's going to make this formant, higher or lower. It is most responsive to labial constriction, like if you close your lips, that is going to affect it, raise it, or it will lower it. Or if you protrude your lips like this, ooh, it's going to affect F1. The F1 is also inversely related to the tongue height. It means, we said F1 is measured here. If the tongue rises in the vocal tract, it will move out of the back of the throat and it will create more space. And the more space that you have, the lower the frequency will be. The smaller the volume is, the higher the frequency, because the air is going to travel faster in a small volume as opposed to a larger one. So now F2, which is R3, it has 2 points of pressure and 2 points of velocity, and it relates to the length of the oral cavities, and especially in front of the tongue, if there's a constriction in front of the tongue. So in other words, it is across from the alveolar ridge, the space between the alveolar ridge and the tongue. This is where F2 is localized. It is most sensitive to the length of the oral cavity. If someone has say the length of the oral cavity, the distance here, that is going to make it low or high, and also tongue advancement. If the tongue goes forward, it will create a smaller space in the front that will make the frequency higher. And if the tongue goes back, it creates more room in front, and that will make the frequency lower for F2. F3, which is the fifth vibration, 5 quarters fitting in to the vocal tract. It is most sensitive to front-back constriction. Like if there's any constriction here in the vocal tract, that's going to affect the third formant. It is localized in this area near where you say ka anga, between the velum and the dorsum or the body of the tongue. That is F3. So these 3 locations, when the wave reaches this area, it is going to be amplified. When it reaches the area here, it will be amplified. When it reaches the other area here, it will be amplified. And the 3 amplifications are played at the very same millisecond. They buzz together, and you hear them just as if they are just one sound. So resonances change frequencies when the vocal tract is constricted near a point of maximum velocity or maximum pressure. So any place that you kind of you change these values, that is going to make to make resonances change. So for example, if there's a constriction at the point of maximum velocity, like at the lips, for example, that is going to lower the resonant frequency. If you say pa, pa, you constrict your lips, that's going to make F1 lower. Constriction at the lips lowers also F2. So constriction at the point of maximum pressure raises resonant frequency. For example, at the in the back of the pharynx. I'm gonna show you how this works. I'm gonna give you examples, but just let me say this first, and then we'll give you examples. And a constriction in the lower pharynx raises F1. So speech sounds that require a small mouth opening, like or in the front sounds, they have a lower F1. The higher the tongue position in the oral cavity, the lower the F1, and the lower the tongue position, the higher the F1. Again, I'm going to give you some examples where it is all about space. If you understand that the greater the volume of air is, the greater the space is, the lower the frequency, and the smaller the space is, the higher the frequency, then if you understand that, you can figure out many of the questions. F1, and at its highest frequency value, is the lowest frequency of the vocal tract, because F1 is the first, or the first formant is the first time that the tube is going to start to resonate, and anything that comes after it is higher than it. So let's say F1, the first time from F1, the second time that you're going to get a response, that will be twice as high. If F1 is, let's say, 500, the second vibration has to be 1000. And then the third is going to go from there. So at its highest frequency, F1 is still the lowest frequency of the entire, all the series. So when you say E, and you say as in man, versus E, let's see what this looks like. When you say E, see what happens to the tongue. It lifts up, goes out, and goes to near the alveolar ridge. So that means, see all the space that it has freed in the back. That creates a larger volume for F1. So for that, as a result, the tongue going out of the way and going up frees the back of the pharynx, the lower pharynx, and that makes F1 lower for E. Let's see. So the formant is basically the line that is used to measure, to mark the first resonant frequency. So for F1, first formant, second formant is here, third formant is here. So formants are these dark bands of energy that are plotted on a spectrogram. So here's another one that is similar to the harmonic series that we looked at, and you go here, F1 here is at 300. So F1 here, if you measure the vibration of the air here, when the wave first starts to vibrate, then that will be 300 times per second for E. The second formant that is across from the oral cavity here, from the alveolar ridge. Now the tongue has filled most of the space. There is not much room there. What do you think? How do you think F2 is going to be? And why? I'll let you answer this question. So now you could see F2 hits at 2500 hertz. See the gap between 300 and all of this is deleted way back here. You are going to get 2500. That is because the tongue action has restricted the space, had left only a little bit of room for the air to vibrate. That raises F2 significantly. Let's see what F3 is like. F3 is here. Again, because the tongue is raised and constricting the space, see F3 comes very, very quickly, unexpectedly at 3000 hertz here. So again, tongue height and tongue advancement have a direct influence on the F1 and F2 and F3. It affects the resonant frequency because it's a matter of room. The greater the space is, the lower the frequency, the smaller the space, the higher the frequency. Now let's look at another scenario. This is ah as in jar or far. In order to make it, this is the sound when you go to the doctor and the doctor would say, would ask you to say ah, simply to make the tongue go down and back out of the way so that they can see the back of the throat. When you say ah, the velum is lifted up so you can see the back of the throat. So this occurs because or by the this is the hyoid bone, this is the back of the tongue. There's a muscle called the hyoglossus. It is oriented at an angle. When it contracts, it brings the tongue down and back. By doing so, you have now freed the front of the oral cavity, created a lot of room. So what do you think about F2 here? What is it going to be like, high or low? What about F3? Now what about F1? So F1, the tongue is being pulled down and back. It has taken room from the lower pharynx. That is going to make the frequency of F1 significantly higher because there is not enough room here. And the other ones, F2 is going to be significantly lower because there's a lot of space, and F3 is going to be lower because there's a lot of space. So it's again, the tongue is the biggest modifier of vocal formants. When we look at the U, I'd like you to understand these sounds because I'm going to have you describe them in the exam. U, there's a muscle called the styloglossus here and here that's going to lift up the tongue and back. So it will make it like that. So now you can predict how F2 is going to be. You can answer this easily. So all of this space is added to F2. How about F3, which would be here? How about F1? So for F1, you have created a little bit of room. However, you just brought the tongue back and constricted the space. So how is that going to affect F1? F1 is going to be influenced by a huge, very long tube. The length of the tube is going to determine how low or high the resonant frequency is. The longer the tube is, the lower the frequency. The shorter the tube, the higher the frequency. So if you get a string and like trace this, the tongue is now acting like a mountain peak. So it makes the trip of the air way longer. And by the time you go to the vocal tract here, I mean the lips, that is the longest vocal tract you can make with any sound at all. Because the tongue just rises and makes the trip very, very long. In addition, the lips are protruded. Ooh, and that makes F1 low. So for ooh, even though the back is constricted, however, the length of the tube overcomes that effect, and it makes F1 as low as 300 Hertz and F2, because of the room here created, 870, and F3 is 2240 Hertz. So the longer the oral cavity is, the lower the frequency to which it will resonate. Now, these things you need to really, kind of get to understand. Tongue backing or lip rounding are going to lower F2 because the constriction occurs near a point of high velocity. Tongue or jaw activity that narrows the areas of higher pressure are going to raise the frequency. So for example, you will have high F2 because if you have short oral cavity, as in E, F2, the tongue goes out and occupies the room, and between the alveolar ridge and the front of the tongue. For ooh, you are going to have a long oral cavity, and that is going to lower the frequency for the F2 for ooh, as in what you are having here. You also have a large space that's created because the tongue is backed. Now, let's look at something that is called source filter theory. And that's it. It helps us understand how speech is produced. And we look at the speech production as a product of a source, which is produced by the vocal folds. They make a buzz, and then a filter. We said the vocal tract acts as a filter because it's a 1/4 wave resonator. It takes out even resonances that yield opposing forces, and it leaves odd multiples that enhance the wave. So it is filtering, it is enhancing the sound waves. So as a result, we call this source filter. How we make speech. The vocal folds vibrate to make tones. These tones cause the air in your vocal tract to vibrate, and that vocal tract will filter out that sound, and this is how we make speech. So the source here is the vocal folds, and the filter is the vocal tract. The vocal tract produces harmonic frequencies that that we know as the Formant frequencies of the vocal tract. The harmonics that are far from the frequencies of the vocal tract, they are attenuated. The harmonics that are close common range within those of the vocal tract itself are going to be amplified, which is saying that the odd harmonics are the ones that match the vocal tract frequency, and they stay, and the even ones do not match and they are attenuated. So in the end, speech that is recorded at the lips has both characteristics of the vocal fold harmonics and the vocal tract harmonics combined together, because all of them play almost simultaneously. So now we look here. If you look at harmonic series, the graph is going to be like this. So on the left, the highest frequency will be the first harmonic to occur, the first harmonic. And then the second one comes is going to be lower in loudness. And each one that's going to come is going to be higher frequency, lower in amplitude, as you could go to a point where the sound is no longer, it is too high to be heard. So that is the normal scenario, like we did before. That's the glottal pulse, the vocal folds, how they make harmonics, like exactly like the string in the video that you watched. That was the glottal, which is from the vocal fold pulses. And nothing is skipped. You just go from 100, 2, 3, 4, and so on. Because there is no filtering at this point. Now the buzz is going to go through the vocal folds, through the vocal tract. And the vocal tract is going to attenuate selectively. So the first response will be at 500. That's the natural resonant frequency of the vocal tract. Then it will attenuate the even ones. 2000 will be left out. And then 1500 will stay. And then 1000 will be left out. 1500 stays. 2000 will be left out. 2500 will stay. 3000 will be left out. 3500 will stay, and so on. So this is how it's gonna be. But now what you hear at the end, at the lips, is a combination of the glottal pulse and the and the resonant frequency of the vocal folds. If you overlap, put these together on, like, what do you call it? There's a term, overlay one on the other, you are going to get this graph. So gradually, as you come close to the natural frequency of the vocal tract, then you enhance and enhance. As you come closer to it, you get the maximum amplification at 500. As you go away from 500, you start to sharply decrease. 1000 is attenuated, and then you rise again gradually to 1500. So this is a combination of this and that, is to say that what you hear at the lips is a combination of vocal fold harmonics and vocal tract harmonics. There are ways to prove that the source with the vocal fold vibration can behave independently from the filter, from the vocal tract itself. How do we do that? If you say or you have a certain pitch, you have a certain resonant frequency when you say and you keep the lips moving the same way, the vocal tract doesn't change. So you basically, if you want, as you continue saying you can't change the vibration rate of the vocal folds, saying So I haven't changed the shape of the vocal tract itself, but I changed the vibration rate of the vocal folds by making them vibrate faster or at a higher frequency or lower frequency. Now, how do I change the filter and keep the vocal folds at the same vibration rate? You simply change from one sound to the other, like this, at the same vibration rate of the vocal folds, and then I go, so E, and then midstream I shift to another sound like E-U, E-U. So my vocal folds are vibrating exactly at the same rate. They have the same fundamental frequency, but now by modifying the shape of my lips and pushing them forward, I changed the vibration rate of the vocal tract itself by shifting from one sound to the other. So these spectrograms, they are used to plot the frequencies, Formant frequencies of sounds in the vocal tract. The lowest one, first, the vertical axis, it shows you from 0 to 8,000, the frequencies. And then the horizontal, it shows you the time it takes to make a sound. And there are machines, hopefully we'll be getting one in the next couple of months in the clinic. When you use a microphone and say, it gives you these Formant values, and it gives you how long it takes. So when you say E, you start here and you end here. It means from here to here is about maybe 2 seconds, real time. And you say ooh, from here to here, it plots the real time that you make the actual sound. So when you say E, you get so many waves together, coming together with all the compressions together, show up as that dark band of energy. The darkest band, the strongest, the loudest, is the lowest one in the series. That band is called a formant. So we say the first formant usually is the lowest, the darkest band in the series here. And then this is for E. We said E occurs at 300, F1. And then as you go F2, you just skip, and F2 is 2500. And then F3 comes right after at 3000. And then F4, you skip and then go up higher. So, and you keep going. For U, you get 300 at F1, and then F2, 870 or so, and then F3, it's about 2500 here, about here, and then F4. So for R, you get F1, because there's constriction, then F1 is high, significantly high, 900 something, and F2 is low, relatively low compared to F1, and then F3 is somewhat low as well. So these bands, again, if you break them down, magnify them, you find them basically the compressions of the of every wave, and they are marked as that dark energy, or it gives you the amplitude. It tells you how much energy there is in that wave, and always the first harmonic, the first formant is the loudest, is the most amplified. As you go up, then it becomes weaker and weaker. These are just transitions. We'll do some more in class, but I'd like you to know the names of the formants and how to calculate, and we'll do more today. Thank you.